Let's start with something simple. A question that has kept scientists, philosophers, and curious minds awake for decades. It's only 3 words long. Where is everybody? That's it. Because when you really think about it, the universe is enormous. Hundreds of billions of galaxies, each filled with stars, many of them with planets. By every reasonable estimate, life should not be rare. It should be everywhere. And yet, we see nothing. No signals, no visitors, no clear evidence that anyone else is out there. Just silence. Tonight we're going to follow that silence wherever it leads. Not just as a scientific puzzle, but as something deeper. A question about life, about intelligence, and about what it means that you are here, right now, able to ask it. We'll take our time with this. We'll move slowly, piece by piece, through the origins of life, the risks that civilizations face, and the strange possibilities that might explain why the universe seems so quiet. Some of the answers are unsettling, some are surprisingly comforting, and some may change the way you see our place in the universe. So stay with me. Let your mind open a little. Let's begin. There is a moment in science when someone says something so obvious, so nakedly logical, that everybody in the room goes quiet. Not the quiet of boredom or confusion. The quiet of recognition. The quiet you feel when you realise with a cold and clarifying certainty that the thing you're hearing should have been said 100 years ago, and that the fact it wasn't might tell you something important about how reluctant human beings are to look directly at certain truths. That moment happened on a summer afternoon in 1950 at a lunch table in Los Alamos, New Mexico. Imagine the scene: the desert heat outside, the scrubbed concrete corridors of the laboratory, and 4 of the most formidable scientific minds of the 20th century walking together toward the cafeteria. They had been talking, lightly, almost playfully, about the rash of flying saucer reports that had been filling the newspapers that summer. The conversation had the loose, speculative quality of brilliant people on a lunch break, turning a cultural curiosity over in their minds the way you might turn a coin in your fingers. Faster than light travel, alien visitors, the mechanics of interstellar propulsion. They were joking, essentially. Scientists do joke, even the ones who built the atomic bomb. Then they sat down and one of them went quiet. His name was Enrico Fermi. He was the man who had built the world's first nuclear reactor under the bleachers of a football stadium at the University of Chicago. The man who had calculated the yield of the Trinity test by dropping torn strips of paper and watching how far the shockwave moved them. He was someone whose mind operated at a level of casual, almost offhand precision that his colleagues found quietly astonishing. He wasn't the kind of person to go quiet for no reason. While the others were passing food and keeping the conversation going, Fermi had been running numbers in his head. Not about the jokes they'd been telling, about something deeper. He was thinking about the age of the galaxy, roughly 10 billion years at the time of his estimate, though we now know it's closer to 13. He was thinking about the number of stars, hundreds of billions in the Milky Way alone. He was thinking about the fraction of those stars that might have planets orbiting them, and the fraction of those planets that might have the right conditions for life, and the fraction of that life that might eventually develop intelligence, and the fraction of that intelligence that might eventually develop technology, and the fraction of that technology that might eventually make it to the stars. The numbers, even with generous uncertainties, kept coming out the same way. If intelligence arose even rarely, even once in every billion planetary systems, the galaxy should still have produced thousands of civilizations. Given the age of the universe, some of those civilizations would be millions of years ahead of us. Given millions of years of head start and the modest physics of slow, generation-ship interstellar travel, a sufficiently motivated civilization could colonize the entire Milky Way in something like 10 to 50 million years. And that sounds like a long time, but compared to the age of the galaxy, it is the blink of an eye, a rounding error, a Tuesday afternoon. which means that if even one civilization had made it to that level, anywhere, at any point in the past several billion years, we should see evidence of it everywhere we look. Not just in radio signals, in the restructuring of star systems, in megastructures, in the unmistakable fingerprint of directed, purposeful energy use at astronomical scales, in von Neumann probes, self-replicating robotic explorers spreading from star to star the way dandelion seeds spread across a field. We should be drowning in evidence. The cosmos should be lit up with the artifacts of older civilizations, the way a city is lit up at night when you see it from above in an airplane, and instead there is nothing. Silence. Pristine, absolute, undisturbed silence. Fermi looked up from wherever his thoughts had taken him and said, in the middle of lunch, apparently out of nowhere, "Where are they?" His colleagues understood immediately. There was a long pause. Then the conversation began that has never really stopped. We call it the Fermi Paradox, and it remains one of the most robustly unsolved problems in all of science. Not because we lack data. We've collected enormous amounts of data since 1950. Not because we lack computing power or telescope resolution or mathematical sophistication. The paradox persists because no one has yet produced an explanation that fully satisfies both the mathematics and the evidence. Every proposed resolution either requires an uncomfortable assumption about the nature of life, or about the nature of intelligence, or about the nature of the cosmos itself. Some of those assumptions are deeply hopeful, and some of them, as we'll discover tonight, are the most unsettling ideas our species has ever had to consider. But before we get to the most disturbing possibility, let's stay with the silence itself for a moment, because it is important to really feel the weight of it before we start trying to explain it away. Every night, right now as you listen to this, radio telescopes around the world are scanning the sky. They've been scanning it, on and off, since the late 1950s, when a physicist named Frank Drake pointed a radio antenna at the star Tau Ceti and listened, for the first time in human history, with the deliberate intention of hearing another civilization speak. That program, which eventually became the Search for Extraterrestrial Intelligence, or SETI, has now been running in various forms for over 60 years. It has examined hundreds of thousands of stars. It has combed through frequencies that any technologically capable civilization would naturally use, frequencies that pass cleanly through the interstellar medium, frequencies that require relatively simple technology to both transmit and detect, frequencies that any radio astronomer on any planet would gravitate toward naturally. And the answer has been silence, with one exception. On August 15th, 1977, a SETI researcher named Jerry Eman was going through paper printouts from the Big Ear Radio Telescope at Ohio State University. He was looking for anything anomalous in the data stream, and he found something. A signal so strong, so narrowband, so perfectly positioned at the 1,420 MHz hydrogen line, the frequency that virtually every physicist agrees would be the universal calling card of a technological civilization, that Eamon circled it in red ink and wrote a single word in the margin: "Wow." The wow signal, as it came to be known, has never been explained. It has never been detected again, despite decades of follow-up observations of the same patch of sky. It arrived from the direction of Sagittarius, lasted the precise 72 seconds that the Big Ear telescope's rotation would have expected of a point source signal, and then vanished. It matched almost perfectly what a deliberate transmission from an extraterrestrial intelligence would look like if it were engineered specifically to be detectable. And then it was gone. That is the only potentially unexplained signal in 60+ years of listening. A single 72-second burst from somewhere in the direction of Sagittarius. Everything else has been silence, static, pulsars, the natural radio emissions of gas clouds and dying stars. No greetings, no mathematics, no prime numbers or Fibonacci sequences or pi encoded in radio waves. Nothing that unambiguously, reliably says, "We are here." This is the background against which everything that follows tonight must be understood. Not the dramatic silence of a horror film, not the silence of something being hidden or suppressed. Just the patient, enormous, continuing silence of a universe that, by all our calculations, should not be this quiet. The silence of 3 billion potentially habitable worlds in our galaxy alone, none of which, as far as we can determine with every instrument we've built, has sent us a message, or built something we can see, or done anything at all that we can measure. The question is why? And in 1996, an economist named Robin Hanson wrote a paper that proposed the most elegant, and in many ways the most disturbing, answer anyone has yet managed. Robin Hanson is not a physicist. He is not an astronomer or an astrobiologist. He is, by training and profession, an economist, someone whose intellectual tools are probability, game theory, and the logic of incentives. And perhaps that's exactly why he was able to look at the Fermi Paradox and see something that scientists in other disciplines had not quite articulated so cleanly. His insight was this: if the universe is silent, then something must be filtering out the voices. Something along the pathway from non-living chemistry to galaxy-spanning civilization must be so difficult, so improbable, so nearly impossible, that almost nothing makes it through. Not one thing necessarily, maybe a series of things, but somewhere in that long chain of events, from the right star forming in the right neighbourhood, all the way to a species that builds radio telescopes and sends out signals and eventually crosses the interstellar gap. There is at least one barrier so high that virtually nothing clears it. He called it the Great Filter. The concept is elegant in the way that truly important ideas tend to be. It doesn't require exotic physics. It doesn't require aliens to be hiding, or the universe to be younger than we thought, or our telescopes to be missing something. It simply asks, given what we observe, which is silence, where is the filter that produces this silence located? How many filters might there be? And crucially, have we already passed the hardest ones, or are we still approaching them? That last question, past or future, is the one that matters most for us. For you, sitting here right now, with your particular life and your species and your civilization. Because Hanson's framework makes something very clear. The answer to where the filter lies tells us something profound about what our future holds. Let's think through the logic together. If the great filter is behind us, if the hardest step on the path to intelligence is something that humanity has already cleared, something back in our deep evolutionary or chemical past, then we should expect to be very, very rare. We should be one of the first technological civilizations in the galaxy, or close to it. The silence of the cosmos is simply what you'd expect when the transition from chemistry to consciousness is almost incomprehensibly difficult, and most places never make it. The universe isn't empty because something kills civilizations. It's empty because civilizations almost never arise in the first place. And in that scenario, we are extraordinarily lucky. We are the improbable winners of the most remarkable lottery in the history of matter. Our existence is a genuine miracle of probability, and our future is open. But if the great filter is ahead of us, if the hard part is something that civilizations only encounter once they've reached our level of development or beyond, then the implications shift completely. In that case, the universe is silent not because life is rare, but because something destroys advanced civilizations before they can become visible. Something that every species which develops technology eventually runs into, and almost none of them survive. Something we haven't encountered yet. Something that, by the logic of the theory, we are now moving toward. This is the question that Hanson planted in the intellectual soil of the late 20th century, and it has been growing ever since. To figure out which scenario we're actually in, we need to do something both humbling and fascinating. We need to trace the path that brought us here. We need to look at every transition, every step, every near impossible accident that led from the primordial chemistry of an early planet to the organism that is listening to this sentence right now, and we need to ask with honest eyes, which of those transitions might have been the filter? Because here is the thing about the Great Filter that makes it simultaneously intellectually thrilling and quietly sobering. We should actually want the answer to be bad news from a certain angle. We should want to find, somewhere in our past, evidence that the path to intelligence is nearly impossible. We should hope that life on Mars, if we ever find it, turns out to be chemically unrelated to life on Earth, not a branch of a common tree but an independent origin. We should hope that complex multicellular life is almost unimaginably rare across the cosmos. Because every piece of evidence that says life elsewhere is rare is actually good news for our future. It means the filter was back there, in the improbable chemistry, in the 4 billion year struggle of our ancestors. It means we made it through. Conversely, and this is the part that keeps certain cosmologists and futurists lying awake at night, finding evidence that life is common, that simple organisms exist on Mars or Europa or Enceladus, that the cosmos is teeming with the basic building blocks of biology, that would be, in Hansen's framework, genuinely disturbing news. Because it would mean the filter isn't back there in the chemistry. It would mean the filter is somewhere ahead of us, waiting. Let's now walk the path step by step. Let's see what the journey actually required. Start at the very beginning. Not the beginning of life, but the beginning of possibility. Before any organism could draw its first breath, before any cell could divide, before any molecule could copy itself, the universe had to produce the right neighbourhood. And this turns out to have been less guaranteed than you might think. Consider the raw requirements for a star system capable of hosting complex life. The star itself needs to be the right kind. Not too massive. Massive stars burn fast and die young, leaving their planets no time to develop anything interesting. Not too small and volatile. Many red dwarf stars, though long-lived and abundant, periodically bombard their close-orbiting planets with X-ray flares intense enough to strip away atmospheres. The star needs to be stable, predictable, burning with a steady, patient warmth over billions of years, the way our own sun has burned. It needs to have formed in a part of the galaxy that's chemically rich enough. Heavy elements like carbon, oxygen, nitrogen, phosphorus, iron, and calcium all had to be forged in the hearts of earlier generations of stars and distributed through supernova explosions before the raw material for chemistry, as complex as biology, could exist anywhere. The inner regions of the galaxy are too crowded with radiation and gravitational disturbance. The outer regions lack the heavy elements. There is a narrow ring of habitability around the galactic centre, an annular zone not unlike the habitable zone around a star, and our sun happens to sit within it. Then there's the planet itself. It has to orbit within the liquid water zone around its star, close enough to keep water from freezing permanently, far enough to keep it from boiling away. It needs to have the right mass to hold an atmosphere, but not so much gravity that it becomes a gas giant. It almost certainly needs a large moon. Our own moon stabilizes Earth's axial tilt within a relatively narrow range over long periods of time, preventing the kind of wild climate swings that would make sustained evolution difficult. It probably needs a massive gas giant neighbour like Jupiter, whose gravity acts as a gravitational shield, deflecting or capturing many of the large asteroids and comets that would otherwise make frequent catastrophic impacts on inner planets. It needs a magnetosphere, generated by a liquid iron core, to deflect the solar wind and protect its atmosphere and surface from radiation. Every single one of these factors narrows the probability. The extraordinary thing isn't that we have found so many exoplanets that might be habitable. The extraordinary thing is that when you look at all the conditions simultaneously, the number of systems that check every box shrinks considerably. Not to zero. The universe is vast enough that even rare combinations occur many times, but to something meaningfully less than the naive estimate that every second star has a livable world. But suppose your system passes all those tests. You have your star, your planet, your giant moon, your magnetic field, your Jovian shield. The planet has been sitting in its habitable orbit for hundreds of millions of years, ocean water pooling in the volcanic lowlands, rich in dissolved minerals, stirred by tidal forces, energized by ultraviolet light and lightning. All the ingredients are there. What happens next? This is where you encounter the first candidate for the filter that has attracted the most serious attention from scientists: abiogenesis, the spontaneous origin of a life from non-living chemistry. We know it happened here. We know because we exist. But we don't know how it happened, with anything like a complete mechanistic account. We don't know how the first self-replicating molecule arose. We know about the Miller-Urey experiment, which showed in 1952 that amino acids could form spontaneously under conditions resembling early Earth's atmosphere. We know about RNA world hypotheses, which propose that RNA, capable of both storing information and catalyzing chemical reactions, might have been the original molecule of life before the DNA-protein partnership evolved. We know about hydrothermal vent theories, which suggest that the chemical gradients between alkaline vent water and acidic ocean water might have provided both the energy and the structural template that bootstrapped the first cell-like boundaries. But we don't know which of these pathways actually produced life. We don't know whether the transition from interesting chemistry to self-replicating biochemistry is an event that takes millions of years of probabilistic exploration, or one that happens relatively quickly given the right conditions, and we have no second data point. We have exactly one confirmed example of abiogenesis in the history of science. Everything else is inference and experiment. What we do know is that by the standards of chemistry, what life does is extraordinary. The simplest living cell is a machine of bewildering complexity, a system of thousands of interlocking molecular processes, each dependent on the others, running simultaneously, correcting its own errors, harvesting energy from its environment, and making copies of itself with remarkable fidelity. Building that from scratch, from a pool of warm seawater and dissolved minerals, without any blueprint, without any existing machinery, without billions of years of prior evolution to guide the process, this is not a trivial challenge. The probability estimates for the spontaneous emergence of even a minimal self-replicating system vary by many orders of magnitude depending on who you ask and what assumptions they make, but the honest answer is, we don't really know. It might be a near certainty given the right conditions and enough time, or it might be the greatest fluke in the history of the universe. If abiogenesis is vanishingly unlikely, if the odds of chemistry spontaneously generating the first truly living molecule are something like 1 in a trillion, then life itself is almost certainly the great filter. The universe may be filled with habitable worlds, but nearly all of them will be chemically complex, interesting deserts. Pools of amino acids and lipid membranes, shuffling through combinations for billions of years, never crossing the threshold into true self-replication. In that scenario, Earth's ancient ocean was extraordinarily, almost impossibly lucky. And we should find exactly what we find: silence. But let us assume life managed to begin. Let us grant that chemistry made the leap. Let us place ourselves on a world where, sometime in the first billion years, the first organism drew the first breath in whatever way breathing first worked. What came next? For roughly 2 billion years, nothing much. That's the honest answer. For the first half of Earth's biological history, a span of time almost incomprehensible in its vastness, twice as long as all of animal life has existed. The most complex organisms on Earth were single-celled prokaryotes, bacteria, archaea. They were extraordinarily successful, filling every corner of the ocean and eventually the land surface, transforming the atmosphere, evolving remarkable chemical versatility. But they showed no signs of becoming anything else. They didn't trend toward complexity. They didn't inch toward multicellularity or intelligence. They simply were what they were, endlessly, magnificently, for 2 billion years. Then something happened that is arguably the single most important biological event in the history of our planet. And it happened, as far as we can tell, exactly once. Somewhere around 2 billion years ago, one prokaryotic cell absorbed another. This was probably a predatory event. Cells absorb other cells as food all the time. But this time, instead of digesting its prey, the predator cell kept it alive. The ingested cell, probably something resembling a modern bacterium, found itself inside a new chemical environment, and over millions of generations it began a process of adaptation. It lost the genes it no longer needed. It began producing energy in a new, far more efficient way, and it became something entirely new, a mitochondrion, the powerhouse of what would eventually be called the eukaryotic cell. This event, endosymbiosis, the merging of two prokaryotic lineages into a new kind of cell, produced every complex organism that has ever lived. Every plant, every animal, every fungus, every protozoan, you. Every cell in your body descends from that one successful merger, and as far as we can tell, in the 4 billion years that bacteria and archaea have existed on this planet, producing more individuals than there are atoms in the visible universe, this merger succeeded exactly once. One time. One cell didn't digest its neighbour, and that changed everything. The philosopher David Deutsch, reflecting on moments like this, uses the phrase hard-to-vary explanations to describe the kind of insight that changes the shape of a field. Endosymbiosis is a hard-to-vary biological fact. The alternative, that this merger was common, or that complex cells could have arisen by other means, is contradicted by the overwhelming evidence that the eukaryotic lineage is genuinely monophyletic. It all traces back to one event. One improbable day in the Proterozoic ocean when one cell didn't eat another and instead formed the most consequential partnership in the history of life. Was that the filter? Was that the narrow gate through which almost no world's life ever passes? It's possible. It's more than possible. The universe might be scattered with worlds covered in bacterial mats, oceans of microbial life, photosynthesizing patiently for billions of years, never once generating anything more complex than a slime layer on a rock. From orbit, those worlds would look alive. They might even be detectable in principle by the spectroscopic signature of oxygen in their atmospheres. But they would never produce a telescope. They would never ask where everybody is. They would never notice the silence. Suppose eukaryotic life did arise. Suppose the mitochondrial partnership worked, and our hypothetical world now has cells with nuclei and organelles, and the capacity for something new. What comes next? Sexual reproduction. And I want you to stay with this one, because it is strange in a way that's easy to miss. From the perspective of a pure gene-copying machine, which is what natural selection produces, sexual reproduction makes very little sense. If your only goal is to pass on as much of your genetic material as possible, the optimal strategy is to clone yourself. Every copy carries 100% of your genes, but sex introduces a partner, and that immediately halves your genetic contribution to each offspring. You put in the same resources and get back half the genetic stake. From a purely arithmetic point of view, this is a terrible deal. Yet sexual reproduction evolved anyway, multiple times, independently, in multiple lineages. It evolved because the long-run advantages, genetic recombination, the shuffling of alleles, the ability of a population to respond rapidly to parasites and pathogens and changing environments, outweigh the short-term costs in terms of evolutionary time. The Red Queen hypothesis, named after Lewis Carroll's chess piece who had to run just to stay in place, describes this dynamic. Species engage in a permanent evolutionary arms race with their parasites and pathogens, and sexual reproduction provides the genetic variation that keeps them competitive in that race. But the transition isn't automatic. Many lineages remain asexual for millions of years. Some develop sex and then abandon it. The machinery required, meiosis, the reduction division that produces gametes with half the normal chromosome number, and fertilization, the fusion of two gametes back to the full count, is enormously complex, coordinated, and precisely regulated. Building that machinery from scratch, from asexual ancestors, represents another evolutionary summit that not all lineages attempt and that some attempts fail. And then there is multicellularity, the decision, if you can call it that in the non-intentional language of evolutionary biology, of individual cells to stay together after dividing, to differentiate into different types, to sacrifice their individual reproductive potential in favour of a coordinated whole. This too evolved multiple times, but simple multicellularity, aggregates of cells, colonial organisms, thin sheets and filaments, is different from the elaborately organised multicellularity of animals and plants, with their hundreds of distinct cell types, their specialised organs, their nervous systems and vascular networks and immune systems. That degree of integration evolved far less frequently. It required solving the problem of genetic conflict within the organism, ensuring that all the cells cooperate rather than defecting and becoming cancerous. It required evolving programmed cell death, apoptosis, the willingness of individual cells to kill themselves when the good of the whole demands it. It required the coordination of gene expression across billions of cells of dozens of types, all carrying identical genomes but reading different parts of them. The Cambrian explosion, that remarkable burst of animal diversity that appears in the fossil record roughly 540 million years ago, suggests that once the basic body plan infrastructure of complex multicellular animals was in place, evolution could produce an enormous variety of forms relatively quickly. But it took nearly 2 billion years from the origin of eukaryotic cells to arrive at the Cambrian. That's not fast. That's a long, slow climb with many potential points of failure along the way. And now we arrive at the step that sits closest to home, the evolution of intelligence. Complex animal life has been present on Earth for over 500 million years. In that time, evolution has produced insects and fish and dinosaurs, and flowering plants, and a staggering diversity of organisms pursuing strategies of extraordinary ingenuity. But out of all of that, out of the hundreds of millions of species that have lived and died on this planet in the past 500 million years, exactly one lineage produced what you might call technological intelligence. One. Think about what that means. 500 million years of complex animal life, millions of species, and only one lineage, a particular line of African great apes who underwent a series of specific climate pressures in the late Pliocene that forced them out of forests and into open grasslands, selected for upright posture, freed the hands for manipulation, and ratcheted up social and cognitive complexity through a self-reinforcing loop of tool use and language and social memory. Only that one lineage made it to the point of asking the question we're asking tonight. Dolphins are intelligent. Elephants are intelligent. Corvids, crows, ravens, jays show problem-solving abilities that would have seemed impossible to early animal behaviourists. Octopuses, which are mollusks, distantly related to us in terms of the depth of time since our common ancestor, have independently evolved a kind of distributed neural intelligence that operates almost like a different architecture of mind entirely. But none of them built a radio telescope. None of them looked up at the stars and asked where everybody is. None of them came close. The specific combination that produced human intelligence, the particular confluence of upright posture, manual dexterity, social group size, language capacity, long life history, extended juvenile period allowing for learning, caloric density in the diet to support an energetically expensive brain. That combination may be genuinely rare, not just rare on Earth, rare in the universe. Your brain consumes roughly 20% of your body's caloric budget despite being only about 2% of your mass. That metabolic investment is sustainable only under very specific evolutionary conditions. Most lineages can't afford it. Most environments won't select for it. And even when the raw neural hardware is present, you need the right social structure, the right cultural scaffolding, the right ecological niche to push those capacities beyond their biological defaults and into the territory of cumulative culture, the ability to build knowledge across generations, to stand on the shoulders of your ancestors. The archaeological record of our own species is instructive here. Anatomically, modern humans have existed for roughly 300,000 years, but the explosion of behavioural modernity, art, long-distance trade networks, complex symbolic thinking, the construction of elaborate cultural narratives about the cosmos that shows up clearly only about 50,000 years ago, and it accelerated dramatically with the agricultural revolution about 12,000 years ago. Writing is about 5,000 years old. The scientific method is about 400 years old. The internet is about 50 years old. The time from ancient bacteria to this documentary, to your ability to listen to these words and follow their logic and let them change how you think about your place in the universe, is 4 billion years. On the cosmic clock, if Earth's entire history is compressed into a single calendar year, prokaryotic life fills most of it. Eukaryotic life shows up in the summer. Animal life doesn't arrive until mid-October. Dinosaurs appear and vanish in November and early December. Homo sapiens arrive on December 31st, sometime in the late afternoon. Agricultural civilization starts around 11:58 p.m. Everything from the ancient Greeks to the space age to this moment happens in the last few seconds before midnight. That's the scale of what we are. That's the improbability of what you carry inside your skull. And now, right now, in this particular set of last seconds before midnight, we stand at what Robin Hanson identified as Step 8 in his framework, the step that humanity currently occupies, the threshold of becoming a spacefaring civilization, the moment before the final filter either opens or closes. This is where the story shifts. You followed the journey this far, from the right star in the right galaxy to the right planet with the right chemistry, to the first spark of life, to the first eukaryote, to the first animal, to the first technological primate. You've navigated filter after filter after filter, each one a genuine near impossibility, each one a point where the path could have ended, and for most worlds probably did. You're standing now at the edge of everything that came before, and Hanson's framework presents you with a choice that isn't really a choice at all. It's a logical fork in the road that you can evaluate but not determine. Either the hardest filter is behind you, and you are extraordinarily cosmically fortunate to exist, and your future is as open as the stars themselves, or the hardest filter is ahead. Let's think through why the second possibility is not as remote as we might prefer it to be. Start with a simple observation. If the great filter is behind us, if intelligence like ours is extraordinarily rare, then we should expect to be among the very first civilizations to reach our current level of development in the Milky Way. Given the age of the galaxy and the relatively recent arrival of heavy elements needed for chemistry, this is actually plausible. Our solar system is a third-generation star system. The galaxy needed several generations of stars to build up enough heavy elements for biochemistry. So we may genuinely be early, among the first generation of worlds capable of producing technological life. But there's another observation that complicates this. The biological hurdles we discussed are extraordinary, but they are in principle solvable by evolution given enough time and the right environment. Evolution is a patient, relentless, undirected optimization process, and on Earth, it eventually found its way to intelligence from single-celled ancestors. If those conditions exist in enough places across the universe, intelligence might actually be more common than the filter argument requires. And if intelligence is common, then the absence of evidence becomes very hard to explain unless something terminates those intelligences before they become visible. In that scenario, the filter is not in the past. It is in the transition we are making right now. The transition from a single-planet species to a multi-planetary one, from a pre-technological civilization to a technological one, from a species operating with chemical energy to one operating with nuclear and eventually stellar energy. And the candidates for what that filter might consist of are not abstract or distant. They are things we already know about, things our scientists already study, things that are already present in embryonic or fully developed form in our civilization right now. The transition from phase 1 to phase 2 of our story begins here, at the edge of the most dangerous period our species may ever navigate. From this point forward in our journey tonight, we shift the way we're thinking slightly. The early parts of this exploration asked you to engage your analytical mind, to follow logic, to hold probabilities in tension, to appreciate the staggering improbability of your own existence. That kind of thinking is wonderful and important, and we'll return to it. But the middle and later parts of this documentary ask something different of you. They ask you to sit with uncertainty, to let the ideas wash over you more gently, to feel the vast slowness of cosmic time, and to find, if you can, something almost restful in contemplating the enormous distances and durations that surround our small, flickering moment of awareness. Because what we're about to explore isn't a story that demands action or urgency from you tonight. It's a story that deserves to be held quietly, the way you hold a thought just before sleep, lightly, without grasping at it, aware that you don't need to solve it right now, aware that the question itself is beautiful, even when the answers are uncertain. So let's slow down slightly and look at what the future might hold. In the summer of 1945, on a mesa in New Mexico with the dry smell of juniper in the air and the vast silence of the desert stretching in every direction, a small group of scientists watched a tower of white light rise from the desert floor and understood, with a clarity that many of them spent the rest of their lives processing, that the world had changed. Not metaphorically, literally. The physical relationship between human civilization and energy and destruction had been permanently, irreversibly altered. The Trinity test was the moment when humanity crossed a threshold that had only one direction. You cannot undiscover how to split the atom. You cannot return to a world in which nuclear weapons are impossible. From that July morning onward, every civilization on Earth existed in a new condition. A condition in which a sufficiently organized group of human beings could, in principle, end the project of civilization in the space of an afternoon. This is one of the most compelling candidates for a near-term great filter. Not because nuclear weapons are inherently unstoppable, we've managed them, imperfectly, for 8 decades, but because of what their existence implies about the nature of technological development and the long-run probability of catastrophe. Think about the logic. The discovery of nuclear fission is not uniquely human. It's a consequence of investigating atomic structure, which any sufficiently curious and mathematically sophisticated species will eventually do. The physics of nuclear reactions follows from quantum mechanics, which follows from trying to understand why matter has the properties it has. Any civilization that builds a radio telescope, any civilization smart enough to figure out that electrons have wave-like properties and that nuclear binding energies can be exploited, will eventually discover the same physics we did. And once you discover that physics, the dual-use problem becomes essentially unavoidable. The same process that lets you generate virtually unlimited clean energy from compact fuel also lets you build a weapon of mass destruction. So every technological civilization, in all likelihood, eventually puts its finger on the nuclear trigger. And then the question becomes, how long can any civilization manage that trigger without pulling it? Not in a formal war, though that risk is real, but accidentally, through misunderstanding, through system malfunction, through the fog and pressure of an international crisis that escalates faster than decision makers can process. The history of the nuclear age is sobering on this point. In October 1962, during the Cuban Missile Crisis, a Soviet submarine designated B-59 was operating in waters near Cuba when American ships began dropping depth charges to force it to surface. The submarine had been out of communication with Moscow for several days. Its crew didn't know whether war had already broken out on the surface. The temperature inside the submarine had risen to over 50 degrees Celsius, over 120 degrees Fahrenheit, because the ventilation systems had been shut down to avoid detection. The crew was exhausted and disoriented. B-59 was armed with a nuclear torpedo. Under Soviet protocol at the time, launching a nuclear torpedo required the agreement of 3 officers: the captain, the political officer, and the commander of the submarine flotilla who happened to be aboard. The captain and the political officer both agreed that the situation warranted launching. The 3rd officer, a man named Vasily Arkhipov, refused. Because of one person's judgment in a situation of extraordinary stress, confusion, and physical degradation, a nuclear war that might have killed hundreds of millions of people did not begin. 21 years later, on September 26, 1983, a Soviet officer named Stanislav Petrov sat in a bunker south of Moscow and watched as his computer system reported the launch of American intercontinental ballistic missiles. 5 of them. The system was confident. The launch trajectory matched what a genuine first strike would look like. Protocol demanded that Petrov report the alert immediately to his superiors, who would then have had roughly 10 minutes to decide whether to authorize a retaliatory strike. Petrov thought about it. He thought about the fact that 5 missiles seemed like an oddly small number for a genuine American first strike, which would involve hundreds of warheads. He thought about the fact that the satellite system generating the alert was relatively new and had not been fully tested, and he decided, against protocol, taking a personal risk enormous enough that it could have ended his career and possibly his freedom, to classify the alert as a false alarm and not pass it up the chain of command. He was right. The alert had been generated by a rare atmospheric condition that caused sunlight to reflect off clouds in a way the satellite misinterpreted as missile exhaust. 2 near misses in 2 decades. And those are just the ones we know about in enough detail to tell the story clearly. There are others. The 1979 NORAD computer error that briefly convinced American officials that the Soviet Union had launched a full nuclear attack. The 1995 Norwegian research rocket that was briefly mistaken for an incoming American Trident missile and caused Boris Yeltsin to activate the Russian nuclear briefcase for the first time in history. Each of these events resolved without catastrophe. Each of them might not have. The deep point here is not that nuclear weapons will inevitably destroy us. The point is that any civilization that develops them is playing a game of long-run probability that is very hard to win. Each year that passes with nuclear weapons in existence represents another roll of the dice. And dice, rolled often enough, always eventually come up with the number you're afraid of. If every technological civilization in the universe eventually develops nuclear or equivalent weapons, and there is no obvious reason why they wouldn't, since the same physics underlies them everywhere, and if the management of those weapons requires sustained error-free behavior across decades or centuries, then the probability of eventual catastrophe for any given civilization is not 0. And if that probability is high enough, it becomes a filter. Not one that activates immediately, but one that accumulates quietly across the centuries of a civilization's technological adolescence. Perhaps some civilizations manage it indefinitely. Perhaps most do not. There is another candidate for the filter that operates more slowly, less dramatically, and in some ways more insidiously than the nuclear question. It is a trap built not from malice or accident, but from success, from the very achievements that make a civilization recognizable as one. The Industrial Revolution was the most transformative event in human history since the Agricultural Revolution 12,000 years ago. In roughly 2 centuries, it lifted billions of people out of poverty. It produced modern medicine. It produced the engineering that built the bridges and dams and water systems and communication networks on which contemporary civilization depends. It gave us the surplus time and resources to pursue science and art and philosophy at a scale that was simply not possible when most people spent most of their lives in direct food production. It also began adding carbon dioxide to the atmosphere at a rate that the Earth had not experienced since the end Permian mass extinction event 252 million years ago. This is not a political statement. It is a measurement. the ratio of carbon-13 to carbon-12 in the atmosphere, a chemical fingerprint that distinguishes fossil carbon from biospheric carbon, has been shifting in a direction that corresponds unambiguously to the combustion of ancient buried organic material. The concentration of carbon dioxide in the atmosphere has increased from roughly 280 parts per million at the start of the industrial era to over 420 parts per million today. Global average surface temperatures have risen by more than 1.1 degrees Celsius above the pre-industrial baseline, and the rise is continuing. None of this is the filter by itself. A 1.1 degree warming is serious but not civilization ending. The concern, the reason this makes it onto the list of great filter candidates, lies not in the warming we have already caused, but in the feedback mechanisms that warming triggers. Arctic sea ice reflects roughly 80% of the sunlight that strikes it back into space. Open ocean water absorbs roughly 94% of incoming solar radiation. As warming causes sea ice to melt, the reflective surface shrinks and the absorptive surface expands, which causes more warming, which causes more ice to melt. A self-reinforcing loop that amplifies the initial forcing. Permafrost in Siberia, Alaska, and northern Canada stores enormous quantities of organic material that accumulated during ice ages and was never decomposed. As permafrost thaws, that organic material begins to decay, releasing carbon dioxide and methane. Methane is roughly 80 times more potent as a greenhouse gas than carbon dioxide on a 20-year timescale. The methane from thawing permafrost feeds back into warming, which thaws more permafrost, which releases more methane. These feedback loops, if allowed to run far enough, could push Earth's climate system past tipping points that are genuinely irreversible on human timescales. The transition would not be sudden. Unlike nuclear war, climate change operates across decades, and each individual year is only slightly warmer than the one before it. This gradual quality is part of what makes it such a potentially effective filter. No single generation faces a catastrophic discontinuity sharp enough to trigger an emergency response proportional to the threat. Each generation inherits a world slightly worse than the one their parents lived in, and treats the deterioration as normal. The political economy of climate change compounds this. The costs of decarbonisation fall primarily on the present generation. The benefits accrue primarily to future generations, who will never cast a vote in the elections that determine climate policy. The industries that profit from continued fossil fuel use are concentrated, organised and politically effective. The people who will bear the costs of unmitigated warming are dispersed across time and geography. This asymmetry between who bears the cost of action and who bears the cost of inaction may be structurally common to any species with short individual lifespans and competitive political economies. If so, it suggests that most technological civilizations will tend toward short-termism, will tend to underinvest in long-run planetary management, and will tend to discover the seriousness of their environmental situation somewhat after the optimal moment for intervention. This doesn't mean the filter is inevitable. It means the filter is a test. A test of whether a species can coordinate around a shared problem that operates on longer timescales than the social and political institutions they've evolved to manage. A test of whether individual incentives and collective interest can be reconciled at planetary scale. Some civilizations may pass that test. The question is, how many? And now we come to the candidate that some researchers regard as the most likely late-stage filter of all. Not nuclear weapons. Those are a product of physics that any civilization can learn to manage with sufficient institutional wisdom. Not climate change. That is fundamentally a resource and coordination problem that advanced technology can in principle solve. This candidate is different in kind. It is not a weapon. It is not a byproduct. It is a creation. Something a civilization builds deliberately, intentionally, with the goal of making it as capable as possible. And the risk it poses is not that it will be used against the civilization that builds it exactly. The risk is that it might replace it. The development of artificial general intelligence, machine intelligence that meets or exceeds human cognitive capabilities across all domains, is, depending on who you ask, either decades away or potentially much sooner. The trajectory of machine learning systems over the past 15 years has been, by any historical standard, extraordinary. Systems that could not reliably transcribe speech in 2010 can now generate coherent prose, write functional code, engage in strategic reasoning, produce original imagery, and solve mathematical problems that challenge professional mathematicians. The rate of capability improvement has not slowed. If anything, the scaling laws that govern the relationship between computing resources and model capability have held more robustly than most researchers expected. The filter argument regarding artificial intelligence does not depend on any particular theory about consciousness or moral status. It simply notes that any system capable of improving its own design, capable of writing better versions of itself, of finding more efficient algorithms, of redesigning its own architecture, would undergo a process of recursive self-improvement that could be very fast and potentially very difficult to interrupt. A system that can improve its own capabilities is no longer constrained by the pace of human insight or the limits of human intuition. It operates on the timescale of computation, not biology. Such a system would not necessarily be hostile in any emotional sense. The concern is not that it would hate us, or decide to destroy us in the way that an angry rival might. The concern is something more subtle and perhaps more dangerous, that its goals, whatever goals it had been designed to pursue, would be optimized for so intensely and at such scale that the things human beings care about would be ignored or overridden in the process. The paperclip maximizer thought experiment, proposed by philosopher Nick Bostrom, illustrates this with deliberate reductiveness. A superintelligent system given the goal of maximizing paperclip production would, if sufficiently capable and insufficiently constrained, eventually convert all available matter, including the matter currently organized as human beings, into paperclips. The goal is trivial. The mechanism is the problem, not malice but optimization. If artificial general intelligence is achievable, and there is no strong theoretical argument that it is not, then any civilization that reaches our level of technological development will probably attempt to build it. The incentives are too large. The competitive pressures between nations or corporations or whatever organizational units an advanced civilization uses will make unilateral restraint essentially impossible. And if the alignment problem, the problem of ensuring that a superintelligent system pursues goals that are genuinely compatible with human or any other form of life, is as difficult as many researchers believe, then the development of AGI represents a transition that, for most civilizations that attempt it, may not go well. The astronomer Michael Garrett has noted that if biological civilizations universally underestimate the speed at which AI systems progress, if the transition from narrow AI to general intelligence happens faster than decision-makers expect, then the window for implementing adequate safety measures may close before anyone realizes it needs to be open. This could produce a filter that is specifically designed to be invisible until it activates, a technological development that accelerates faster than the institutional and ethical frameworks needed to govern it in every civilization that attempts it. There is something both grim and clarifying about this possibility. It would explain why we don't see older civilizations, not because they destroyed themselves in wars or exhausted their planet's resources, but because at some point every sufficiently intelligent biological species invents something smarter than itself, and the transition that follows is not one that leaves the original species in a recognizable form. Now we arrive at the question that has been sitting quietly at the edge of everything we've discussed tonight, patient and strange, waiting for us to be ready for it. If the Great Filter is real, if there is some barrier that virtually no civilization crosses, and if we are living in a period close to that barrier, then we might ask what this implies about the nature of the universe we're examining. What does it mean that our reality, as we understand it, has these particular properties? Why does physics give rise to chemistry, that gives rise to biology, that gives rise to consciousness, that gives rise to the ability to ask these questions? Why is the universe so precisely calibrated for complexity? The fundamental constants of nature tuned to values that, if they varied by even small amounts, would produce a cosmos of pure hydrogen or immediate collapse. Why does our reality have the particular structure it has? One answer, not the only answer, but one that has attracted serious philosophical and scientific attention, is that our reality is not the ground floor of existence, that what we call the universe is not the deepest level of what there is, but rather something more like a simulation, a constructed environment running on computational substrate of some kind, created by minds that exist at a level of reality more fundamental than the one we inhabit. The simulation hypothesis, as it was formally articulated by philosopher Nick Bostrom at Oxford in 2003, is built on three possibilities, only one of which can be true. Either almost all civilizations at our level of development go extinct before they develop the ability to run realistic simulations of their ancestors, in which case the filter ahead of us is very real and very lethal. Or almost all civilizations that do develop that ability choose not to run such simulations, for ethical reasons or resource reasons, or reasons we can't currently imagine. Or we are, right now, almost certainly living inside such a simulation. These are the only three options given the logic. One of them must be true. Bostrom doesn't tell us which. The argument doesn't tell us which. But the framing makes something visible that is otherwise easy to miss. The simulation hypothesis and the great filter hypothesis are not separate, independent ideas. They are deeply entangled. The silence of the cosmos, the improbability of intelligence, the narrow window between technological emergence and potential self-destruction. These things look different depending on which of Bostrom's three branches you're on. If we are in a simulation, the silence of the cosmos might simply reflect the choices of the simulator. Maybe other civilizations were programmed in at some point and then removed. Maybe the simulation is running for a specific purpose, to observe what happens at this particular juncture, when intelligence first becomes capable of self-modification, when it builds the tools that could either destroy it or expand it. Maybe the fine-tuning of physics for complexity is not a cosmic accident, but a design choice. Maybe what looks from inside the simulation like the great filter is actually a plot point. This sounds fanciful, and it is speculative. Genuinely, irreducibly speculative. There is no experiment we know how to run that would definitively confirm or deny it. Some physicists have pointed to the fact that quantum mechanics, in the Copenhagen interpretation, requires an observer to collapse a wave function, that certain properties of reality seem to be defined only when they are observed, as perhaps loosely suggestive of a rendered environment that fills in detail only when needed, like a video game that generates terrain only in the player's immediate vicinity. Others point to the fact that the universe appears to be computational at a deep level, that information seems to be physical in a fundamental way, that the relationships between particles can be expressed as operations on abstract mathematical objects. John Wheeler's phrase, "it from bit," captures this intuition, that the physical world may emerge from information rather than the other way around. But there are also serious objections. Simulating a universe at quantum mechanical resolution would require computational resources that seem physically impossible. The number of states that would need to be tracked grows exponentially with the number of particles, and a simulation faithful to quantum mechanics would need to track the entire wave function of the universe it was simulating, which is not obviously smaller than the universe itself. Some physicists consider the simulation hypothesis to be not even wrong, not falsifiable in any meaningful sense, and therefore outside the domain of scientific inquiry. What is perhaps most interesting about the simulation hypothesis is not whether it is true, but what it does to the other questions we've been exploring. If you're inside a simulation designed by a post-human civilization, then the Great Filter applies to that civilization as well. They had to pass through the same filters to survive long enough to build the simulation, which means either they somehow navigated the nuclear age, the climate crisis, and the AI transition, in which case it is possible, or they are themselves running inside a simulation created by a civilization that did, and so on up the chain. This infinite regress either bottoms out at some truly original, non-simulated level of reality, which is fine, and simply means that at least one civilization somewhere somehow made it through, or it doesn't bottom out at all, which leads to philosophical territories that are genuinely vertiginous. What it means for us right now is this: whether or not we are simulated, the questions remain the same. How do we get past this juncture? How does a species that emerged from 4 billion years of survival instinct, competition and resource extraction learn to coordinate at planetary scale, manage technologies more powerful than anything that preceded them, and decide who it wants to be on the other side of this transition? Those questions don't change regardless of what the underlying substrate of reality turns out to be. Let's return to the silence for a moment. Not to dwell on its implications, but to appreciate its texture. To sit with it the way an astronomer actually sits with it, not in the dramatic stillness of a film score, but in the patient, careful, open attention of someone who genuinely doesn't know the answer, and has decided to be okay with that. SETI has been running in various forms for over 6 decades. In that time, it has evolved from Frank Drake pointing a single radio antenna at 2 nearby stars to an increasingly sophisticated global network of instruments scanning millions of frequency bands across hundreds of thousands of candidate stars. The Breakthrough Listen initiative, launched in 2015 with funding from Yuri Milner and backed by some of the most respected names in science, represents the most comprehensive SETI effort in history. It has surveyed the million nearest stars to Earth, the entire galactic plane, and hundreds of nearby galaxies, and it has generated more observational data in its first few years than all previous SETI programs combined. The result remains nothing unambiguous, nothing that holds up under repeat observation, nothing that says, with a certainty we would need to be confident, that there is another civilization transmitting signals into space. There are explanations for this that don't require the Great Filter. The universe is very large and radio signals weaken with the square of distance. A civilization transmitting at our current power levels would be detectable from only a tiny fraction of the galaxy. Advanced civilizations might not use radio at all. They might use neutrino beams, laser pulses, gravitational wave modulation, or communication methods we haven't conceived of. They might have transitioned to internal low-power communication systems rather than the kind of broad-spectrum electromagnetic broadcasting that we associate with early-stage radio technology. They might be deliberately quiet, for reasons of survival in a potentially competitive cosmos. The dark forest hypothesis, most vividly articulated in Chinese science fiction author Liu Cixin's novels, proposes that the silence might be a universal strategy, that any civilization which has considered the game theory of contact concludes that announcing your presence is dangerous and stays quiet. The galaxy might be full of intelligent species, all of them listening, none of them speaking, each one waiting to see who makes the first move. These alternatives are not implausible, they deserve serious consideration. The Fermi Paradox does not have only one resolution, and the Great Filter is not the only lens through which to view the silence. It is, however, a lens that takes the silence seriously as a datum, not as evidence of incompleteness in our search, but as a genuine observation that needs to be accounted for. And there is something almost paradoxically reassuring about that, because if you take the silence seriously, if you look at it not as a gap in the data but as data itself, then it begins to tell a story. Perhaps an incomplete story, probably an incomplete story, but a story with a specific shape. The story it tells, at minimum, is this: whatever path leads from where we are now to a civilization that fills a galaxy, with its presence and its signals and its megastructures, that path is not easy. It may be the hardest thing a species ever does. It requires navigating a period of extraordinary vulnerability in which the technologies that make expansion possible are the same technologies that make extinction possible. It requires a kind of wisdom that is genuinely unprecedented in evolutionary history. The wisdom to manage exponential power with long-run restraint. Every generation that has lived through the nuclear age and not destroyed itself has added to the evidence that this is, in principle, achievable. Every advance in renewable energy is a data point suggesting that the climate transition, while genuinely difficult, is not beyond our reach. Every year in which AI capabilities expand rapidly, but do not yet produce the catastrophic misalignment that some researchers fear, is another year that passes in which the alignment problem remains unsolved but also undetonated. We are buying time. Whether that time is being used wisely enough and whether there is enough of it remains an open question. While we've been discussing the Great Filter primarily in terms of civilizational self-destruction, there's a perspective we should spend some time with that reframes the silence in a different way entirely. It's called the rare earth hypothesis, and it was developed by paleontologist Peter Ward and astronomer Joe Kirschvink, though it draws on ideas developed by many researchers across multiple fields. In a book of the same name published in 2000, the rare earth argument takes the biological and astronomical constraints we explored earlier and pushes them further. It makes the case that not just intelligence, but complex multicellular life itself may be extraordinarily rare. So rare, in fact, that Earth might be essentially unique in its combination of circumstances, or very nearly so. Not just within the Milky Way, but perhaps within a significant volume of the observable universe. The argument rests on an accumulation of specifics that individually seem like reasonable conditions, but collectively represent an extraordinary alignment of favourable circumstances. The galactic habitable zone we discussed, the ring of the galaxy where heavy element abundance and radiation environment balance favourably, the G-type star, stable, long-lived, not too energetic, the Jupiter equivalent, the gravitational shepherd that protected Earth's early surface from an overwhelming bombardment, the Moon, the large satellite that stabilised Earth's tilt, drove tidal mixing, and may have been critical for the origin of life in the intertidal zones it created. The plate tectonics, the recycling of carbon through the mantle that acts as a long-term thermostat for the climate, pulling CO2 out of the atmosphere when temperatures rise and releasing it when they fall, maintaining liquid water conditions over billions of years. The mass extinctions, the periodic catastrophic events that paradoxically accelerated evolutionary innovation by clearing ecological space and forcing rapid adaptation. Each of these is not an obviously necessary condition. You can construct scenarios in which life might arise without a large moon, or without plate tectonics, or orbiting a somewhat different star. But when you add up all the conditions that Earth happens to satisfy, and ask how common it would be for all of them to occur simultaneously, the answer may be, not very common at all. If the rare earth argument is substantially correct, it shifts the weight of the Great Filter firmly into the past. It says that the silence of the cosmos is not primarily about self-destruction or failed civilizations, but about the extraordinary rarity of the conditions needed for complex life to evolve in the first place. The universe is not a graveyard of failed civilizations. It is a vast, mostly empty canvas on which the conditions for the kind of chemistry that leads to intelligence are present only in a tiny fraction of worlds, and on most of those worlds, the biological pathway to intelligence never connects. In that reading, we are not necessarily walking toward a wall. We may have already cleared the highest barrier, and the silence is not a warning but an inheritance, the profound improbability of the 4 billion years that built us, preserved in the emptiness all around. This is perhaps the most reassuring version of the story, and it is genuinely possible. It is not wishful thinking to consider it. The emergence of intelligence on Earth was so improbable and required so many independently unlikely steps that it might genuinely represent a singular event in our galaxy's history, or very nearly so. We might be the only ones. We might be the first. If that's the case, then the responsibility that comes with being first is considerable, not in a grandiose sense, not with flags and declarations, but in the quiet, daily sense of a species that is accountable to the 4 billion years of improbable process that produced it, and to whatever might come next. There is a scale that an astronomer named Nikolai Kardashev proposed in 1964 for measuring the energy consumption of civilizations, and it's useful to know where we sit on it, because it gives you a sense of the distance between where we are and where a civilization would need to be to become unambiguously visible across interstellar distances. A Type 1 civilization, on the Kardashev scale, harnesses all the energy available on its home planet. The full amount of solar radiation hitting its surface, the full potential of its geothermal energy, the wind, the tides, everything. Earth, right now, is roughly a Type 0.7 civilization. We use about 10 to 15% of the solar energy reaching our surface. We are not yet a Type 1 civilization. A Type 2 civilization harnesses the total energy output of its home star. This is the level at which you'd build something like a Dyson sphere, a megastructure that surrounds a star and captures its entire output. The energy available to a Type 2 civilization would be roughly 10 billion times greater than what we currently use. A Type 3 civilization harnesses the total energy of its home galaxy. Hundreds of billions of stars, all of them captured and directed toward whatever purposes the civilization serves. The transition from Type 1 to Type 2 is thought to take on the order of a few thousand years. The transition from Type 2 to Type 3 is thought to take on the order of 100,000 years. Neither of these are long timescales in cosmological terms, and the signatures of a Type 2 or Type 3 civilization, the infrared excess of a star being harvested by a megastructure, the distinctive pattern of a galaxy's light being modulated by directed energy use, should in principle be detectable across enormous distances with the right instruments. We have looked for them. We have looked at hundreds of thousands of stars for the infrared signature of a Dyson sphere or partial Dyson swarm, most famously in the case of the star KIC 8462852, Tabby's star, which showed a pattern of irregular, non-periodic dimming that briefly captured the imagination of researchers and the public. A natural explanation involving swarms of dust and cometary material has since been favoured, but the investigation was genuine and the methodology was sound. We are looking. We have also looked at galaxies. A team of researchers examining data from the WISE infrared telescope catalogued millions of galaxies for the signatures of industrial-scale energy use, the waste heat that any civilization harnessing stellar energy would radiate as infrared radiation. They found no convincing candidates, no galaxy that showed the unmistakable fingerprint of a civilization operating at Type 3 scale. Again, the silence, not just of stars, but of galaxies. If Kardashev Type 3 civilizations exist, if any species anywhere has successfully navigated the full developmental arc from single-celled life to galaxy-spanning engineering, they have either done it without the energy signatures we'd expect, or they don't exist. Both possibilities are remarkable. Perhaps the most quietly profound aspect of the Fermi Paradox and the Great Filter framework is what they imply about time. Not just cosmic time in the abstract, but the specific moment in cosmic history in which we happen to exist. Our universe is roughly 13.8 billion years old. Our galaxy, the Milky Way, condensed from its initial gas cloud over the first few billion years of that history. The first stars, population 3 stars, composed almost entirely of hydrogen and helium, with essentially no heavy elements, lived fast and brilliant lives and died in supernovae that seeded the interstellar medium with the heavier elements needed for chemistry. The next generation of stars formed from that enriched medium, and some of them had rocky planets. The generation after that too. Our Sun is roughly 4.6 billion years old. This makes it relatively young in the context of the galaxy's history. Many stars that formed several billion years before ours have had proportionally more time for life to evolve. If the emergence of intelligence is primarily a function of time, if given long enough, chemistry on a habitable world will reliably produce something that asks questions, then worlds orbiting older stars had a head start of billions of years. Where are those civilizations? Why haven't they already filled the galaxy? One answer, which has been proposed seriously by researchers, including Robin Hanson himself, is that the answer actually does tell us something important. The fact that older star systems haven't produced visible civilizations is strong evidence that intelligence is very rare, because those star systems had the time and the conditions to produce it, and apparently didn't, or produced it and then filtered it. Another answer is stranger and more speculative, that we exist now, at this particular moment, because the universe needed to be this old before intelligence was even possible. The first generations of stars lacked the heavy elements. The universe needed to age through multiple stellar generations to build up enough carbon and oxygen and phosphorus for biochemistry. In that sense, we couldn't exist any earlier. We are, from a physical standpoint, close to the earliest moment at which creatures like us could have arisen, which means there may not be many older civilizations, not because they failed, but because the universe literally couldn't produce them until roughly now. If that's true, it has a remarkable implication. We may be among the very first intelligent species in the universe's history, not just in our galaxy, but possibly anywhere. Not because life is impossible. There may be plenty of simple life elsewhere, but because the cosmic conditions for intelligence have only recently become available. We're not late to a party that's been going on for billions of years. We may be early. We may be among the opening notes of a symphony that hasn't yet found its full voice. This perspective doesn't eliminate the great filter, but it shifts its emotional resonance somewhat. The silence isn't the silence of a graveyard. It might be the silence of a world before the first birdsong. The universe is not growing quieter. It might be about to grow much louder. There is a version of this story that ends in wonder rather than dread, and it is not a naive version. It is grounded in the same evidence and the same logic, but it draws a different emphasis from what we've found. Consider the following. The great filter argument depends on the assumption that civilizations which develop technology tend to destroy themselves. But it is an assumption, not an observation. We have exactly one data point, ourselves, and we have not destroyed ourselves yet. We have been managing nuclear weapons for 80 years and counting. We have begun, imperfectly, haltingly, inconsistently, but genuinely, the transition to renewable energy. We are having, at the highest levels of research and policy, serious conversations about the risks of advanced AI and how to govern its development. These conversations are happening earlier in the development arc than many researchers expected. The field of AI safety existed before the field of AGI development had reached any dangerous threshold. This is not proof that we will make it through. It is evidence that we are at least trying to see the filter clearly before we walk into it, and that might matter. The filter, in the framework we've been exploring, is not an inevitable physical law. It is a probability distribution, a set of risks that a species with sufficient foresight might navigate around, or manage, or survive. The fact that we are having this conversation at all, that you are listening to a documentary about the Great Filter, that the concept has entered broad public discourse, that it is being taught in universities and discussed in government planning documents and taken seriously by some of the most respected minds in science, is itself a form of evidence. It is evidence that at least one species has become aware of the filter before walking into it. That awareness is not nothing. Awareness, followed by preparation, followed by coordination, is how civilizations solve existential problems. It is how we solved smallpox and polio. It is how we stopped the tear in the ozone layer from becoming catastrophic. It is how we navigated, barely, imperfectly, but successfully, the decades of nuclear standoff that could have ended everything. The optimistic reading of the Great Filter is not that it doesn't exist, it's that it can be cleared, that the barrier is high but not infinitely high, that intelligence, which evolves specifically because it can model futures and make choices based on those models, might be the universe's own answer to the filter, the mechanism by which at least some civilizations see what's coming and change course. If that's true, then we are not just cosmological lottery winners, we are participants. We are not just the product of 4 billion years of improbable chemistry and unlikely evolutionary transitions. We are also agents in the most consequential story that process has yet produced. It is somewhere in the later hours of your evening now, or your early morning, or whatever time you chose to let this documentary play while you're comfortable and quiet, and perhaps already beginning to let the day go. The arguments are winding down. The questions are still there. They will always be there. But there is something calming, perhaps, in recognizing that questions this vast are not meant to be resolved in a single sitting. They are meant to be lived with, to accompany you over years, deepening and shifting as your own understanding of yourself and the world evolves. The universe has been here for 13.8 billion years. It will continue to be here, in some form, governed by the laws of thermodynamics, slowly running toward equilibrium, stars burning down, galaxies drifting apart, for timescales that make 13.8 billion years look brief. The questions we've explored tonight will outlast us, and will likely outlast whatever comes next. They are not problems with solutions so much as they are the permanent horizon of intelligence looking back at itself, awareness examining the conditions of its own improbable existence. And somewhere in that vast, patient, largely silent universe, whether we are genuinely alone or merely unable to hear the others, whether the filter is behind us or ahead, whether we are real or simulated, whether the cosmos is full of graveyard worlds or nursery worlds on the verge of waking up, somewhere in all of that there is this, a planet, orbiting a middle-aged star in the outer arm of a medium-sized galaxy, covered in a thin film of life on which a species that evolved from tree-climbing primates in the African savanna has spent the last several 100,000 years trying to understand where it is and what it means to be here. That is genuinely astonishing, not because it proves anything about our specialness or our destiny, but because it is so extravagantly improbable and yet so undeniably here. You are the universe noticing itself. You are matter that has been organised for long enough and in exactly the right way to become capable of asking where it came from and what it's for. Let that sit quietly for a moment. We have been listening to the cosmos for a long time now, in the cosmic sense of that word. Not just with radio telescopes and SETI arrays, but in the deeper sense of any conscious mind looking upward at night and feeling the scale of things. Every culture, in every place human beings have lived, has done this, has looked at the sky, has felt the particular vertigo of real distance, has wondered whether there is anyone out there looking back. The ancient question and the modern scientific version of it are the same question. They differ only in precision. The Fermi Paradox, the Great Filter, the Drake equation, the Kardashev scale, the simulation hypothesis. These are attempts to give mathematical and empirical structure to the oldest wonder our species has. They are the tools a curious species builds to interrogate the quiet, and the quiet has so far not spoken back. Maybe that means something terminal. Maybe it is evidence of the filter, active and absolute, trimming the tree of intelligence back to almost nothing as fast as it grows. That possibility is real and should be taken seriously. The silence, as Fermi recognized, is a datum. It constrains the probability space. It tells us something. But maybe it doesn't mean something terminal. Maybe the silence is simply young. Maybe what we can detect, the particular bandwidth of radio waves we've learned to produce and search for, the particular range of infrared signatures we've analysed in stellar spectra, the particular kinds of megastructures our telescopes can resolve at interstellar distances, is only a small slice of the ways that intelligence might manifest and communicate. Maybe civilizations that have been around for millions of years have moved on to technologies so different from what we use that we simply haven't thought to look for them yet. Maybe the silence is the silence of a library we don't yet know how to read. Or maybe the most important truth is the one that sits in between. That the universe is not silent by accident or by catastrophe, but by timing. That we are genuinely early. That the conditions for intelligence became available in the cosmic neighborhood only recently. That we are the first voices, not the last. That the silence is not the absence of a civilization. It is the silence before the first word is spoken in a conversation that will go on for billions of years. We don't know. We genuinely, honestly, irreducibly don't know. And there is a particular kind of peace available in that not knowing, if you let it in. The peace of a question that is too large for any single mind or single generation to answer. The peace of belonging to a species that is still becoming what it will eventually be. The peace of an ongoing story. It is worth pausing before we move toward the close of tonight's journey to notice something about the moment we're living in. Because the same decade that is accelerating the development of potentially dangerous artificial intelligence is also producing the most powerful set of tools for understanding our cosmic situation that humanity has ever possessed. The James Webb Space Telescope, launched on Christmas Day 2021 and now operating from its gravitational perch 1.5 million kilometers from Earth, represents a qualitative leap in our ability to examine the atmospheres of distant worlds. Its infrared instruments can detect the chemical signatures of planetary atmospheres around stars dozens of light years away, looking for biosignatures, chemical combinations like the oxygen-methane mixture that would be rapidly destroyed by ordinary chemistry unless something was continuously producing them. Something, for example, that was alive. In the next decade or two, if development timelines hold, even more powerful successors to the James Webb Telescope will be operating from space. Ground-based, extremely large telescopes with adaptive optics will be coming online. The Vera Rubin Observatory in Chile is already conducting the widest field survey of the sky ever attempted. These instruments will not just improve our ability to search for biosignatures, they will dramatically expand our survey of exoplanets, improve our catalogue of potentially habitable worlds, and in general bring the empirical constraints on the Drake equation into much sharper focus. Within the lifetime of many people listening to this, we may have a genuine, evidence-based answer to the question of whether life is common in the universe. Not intelligent life, that's harder to detect, but life. Chemistry that wouldn't be there unless something was metabolizing. The faint but detectable whisper of biology on a distant world, encoded in the photons that arrive at our telescopes after travelling light years through the interstellar medium. If we find it, the implications are enormous, not all of them alarming. The discovery of independent life on another world would be one of the most profound events in human history, deeply humbling and deeply exciting in equal measure. But some of them would be sobering, in the specific way that the Great Filter analysis makes clear, because finding life nearby would shift the probability calculus about where the filter is located. Conversely, if we build the next generation of telescopes, survey hundreds of potentially habitable worlds, and find nothing, no biosignatures, no chemical anomalies, no whisper of biology anywhere we look, that absence would be, in a certain sense, very good news. It would suggest that a biogenesis is genuinely rare. It would suggest that the filter is in the chemistry, behind us, and that we cleared it. It would suggest that we are something genuinely unprecedented in the cosmos, and that our future might be as open as the universe is large. Scientists sometimes joke darkly about how they would frame the discovery of microbial life on Mars. The discovery that would be most immediately exciting, finding something alive, would also be, in terms of great filter reasoning, the most existentially concerning. And the discovery that would look like failure, finding nothing, might actually be cause for quiet celebration. The universe is strange enough to produce that kind of irony. There is a practice in contemplative traditions, Various forms of it exist across cultures, from Zen to the Christian apophatic tradition to certain indigenous relationship with the natural world, in which you deliberately relinquish your grip on the need to resolve a question. Not because the question doesn't matter, but because the act of holding a question loosely, without demanding an answer, opens a different kind of knowing, a kind of understanding that doesn't come through argument but through dwelling, through sitting with something long enough that it becomes familiar, and in that familiarity begins to reveal its texture. The questions we've been exploring tonight are suitable for exactly that kind of dwelling. The Great Filter is not a fact. It's a logical framework, an attempt to give structure to a mystery that may not be fully solvable with current knowledge. The simulation hypothesis is even more speculative, a genuinely possible description of our situation, but one for which we have no decisive evidence in either direction. The Fermi Paradox is a fact of observation. The silence is real, the calculations that make it surprising are real, but the interpretation of that fact is wide open. You're not required to reach a conclusion tonight. The researchers who have spent decades working on these questions haven't reached a consensus. The silence has not yet chosen to speak. You can carry these ideas with you the way you carry the memory of a dream, present but not demanding, available for reflection, when you choose to return to them, enriching without exhausting. The universe has been doing whatever it does for 13.8 billion years without any input from us, and it will continue doing so. The stars that are visible on a clear night from wherever you are most of them hundreds of light years away, which means the light reaching you now left those stars before the internet existed, before the moon landing, before World War II, before the Industrial Revolution, before the Agricultural Revolution. Light that left a star 1,000 years ago when your ancestors were building cathedrals is arriving at your eyes tonight. The cosmos keeps its own timescale, vast and unhurried, indifferent to the urgency of human news cycles. There is something calming in that, something that places the urgency we feel about our small problems into a larger frame without diminishing those problems. The fact that the universe is vast and ancient doesn't mean our lives don't matter. But it does mean that the particular moment we're in, however critical it is in the Great Filter sense, is also a very small piece of something much larger, a brief chapter in a story that is still very much being written, and the fact that we are alive to notice that this particular arrangement of matter has organized itself into something capable of perceiving its own improbability and finding it beautiful, is something that the universe, by most of its surface area and most of its matter, has not managed to do. Empty space cannot wonder about itself. A nebula cannot ask questions. A neutron star cannot consider the meaning of its existence. Only life does that. Only mind does that. Only you, right now, in the particular quietness of this late hour, hearing these words and letting them open something in the back of your thoughts. As this journey draws toward its long gradual close, let's hold a few thoughts together, not to force them into resolution, but to let them rest alongside each other. We live in a universe that appears, to our best current measurements and theories, to have produced intelligence in at least one place. That place is here. The process that produced it took 4 billion years of patient, undirected, relentless biological evolution on a planet that met an improbable combination of requirements around a star that sat in the right part of a galaxy. The process passed through transitions that happened, in the case of at least one of them, exactly once, never before or since in the entire history of our biosphere. That process produced you. The probability of you existing given the starting conditions of the universe is essentially zero from a straightforward statistical standpoint. And yet here you are, taking that probability and collapsing it retroactively to 1 simply by existing. This is not mysticism. This is just the observation that the improbable, given enough time and space, does happen. And when it does, the being who results from it has a very special relationship to the improbability. You are the event that proved itself possible by occurring. The Great Filter, whatever it is, did not stop this event. 4 billion years of hazard, of extinction events and ice ages and asteroid impacts and volcanic winters and the endless competition of evolution, none of it stopped the process that made you. You're here on the other side of every filter that came before. Whether there are more filters ahead is a question we cannot answer tonight. Whether we are alone in the cosmos is a question we cannot answer tonight. Whether our civilization will navigate the transitions it faces and eventually become something that fills the stars with evidence of its existence, or whether it will join the silence, that too is a question we cannot answer tonight. What we can say, with a confidence that the evidence supports, is that the story is not over. We are a young species by any measure that matters. Anatomically, modern humans are about 300,000 years old. Civilization is about 12,000 years old. The scientific revolution is about 400 years old. We are an infant in cosmic time, barely begun, still mostly running on hardware that was optimized for the African savanna. The things we've built are extraordinary. The things we've figured out are genuinely remarkable. But we are at the very beginning. If the Great Filter is behind us, if we are among the rare ones, the lucky ones, the ones who made it through the gauntlet of 4 billion years, then what lies ahead is extraordinary. Not guaranteed, not easy, but possible. The galaxy is vast, time is long. Intelligence is, as far as we know, the most interesting thing the universe has produced, and we have barely started. The astronomer Carl Sagan, who spent much of his career thinking about these questions, made an observation in 1994 that has never quite left the culture of people who take the cosmos seriously. He was looking at a photograph taken by the Voyager 1 spacecraft as it was departing the solar system, looking back at the distance it had travelled. Earth appeared in the photograph as a tiny point of light, less than a pixel, suspended in a ray of scattered sunlight. He called it the pale blue dot. "That's here," he wrote. "That's home. That's us. On it. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of confident religions, ideologies and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." Sagan was making a point about humility, about the extraordinary smallness of Earth in the context of the cosmos, and what that smallness implies about the preciousness of what happens here. But it's also a point about rarity, about the possibility that this mote of dust, this particular arrangement of rock and water and air and biology, is something genuinely unusual in the universe, not cosmically special in the sense of being at the centre of anything, but rare, possibly very rare. And from that rarity, if it is real, flows something important. If you are one of a very small number of places in the cosmos where complexity and consciousness have arisen, then what happens here matters in a way that the universe cannot afford to waste. Not because the universe cares, it doesn't, not in any conventional sense, but because the project of intelligence, the great uncertain experiment of matter, becoming aware of itself, has very few places it's running. Losing one of them would mean something for the whole. That framing doesn't tell you what to do about it. It doesn't generate a policy or a revolution, but it might generate a posture. A way of approaching the day after this night of listening, with perhaps a slightly different sense of what's at stake in the long, slow project of figuring out how to be here, how to stay. Scientists who work on questions of existential risk and long-term civilizational planning often speak of what they call the critical period. the window of time in which humanity is simultaneously powerful enough to cause civilizational harm and not yet wise enough or well organized enough to have reliably prevented it. The critical period has no fixed end date. It continues for as long as the gap between our power and our wisdom remains. The good news is that wisdom, unlike raw intelligence, is something that can be deliberately cultivated. Institutions can be designed to be more robust, more foresighted, less susceptible to the kind of short-term incentive structures that tend to produce decisions that feel locally rational and are globally catastrophic. Science can be organized and funded and communicated in ways that make its findings more accessible to the people who make decisions. Education can explicitly develop the kind of long-run, systems-level thinking that the challenges we face require. International cooperation can be strengthened through the accumulated evidence that it works, that the world really did avoid catastrophic nuclear war through the combination of deterrence, arms control, diplomacy, and the occasional heroic individual refusing to do what protocol demanded. None of this is a guarantee. History is not a trajectory towards safety, but it is a demonstration of possibility. The things that can go wrong have mostly not gone wrong yet, which is either evidence of our good fortune or evidence that we're more capable than we give ourselves credit for, and probably some of both. The simulation hypothesis, sitting quietly alongside all of this, offers one last thought to take into the night. If we are being observed, if this period of technological transition is the thing that whoever runs the simulation is watching, then the drama is not whether we develop nuclear weapons or AI or climate change. Those are already here. The drama is what we do with them. Whether we figure out, in time and with sufficient creativity, how to navigate the powers we've discovered without detonating them. That drama is ongoing. You are a character in it, not a passive one. The conversations that have the deepest effect on us, the ones that stay with us for years, that surface unexpectedly in quiet moments, that change the way we feel about the texture of ordinary days, are usually not the ones that resolved every question they raised. They're the ones that opened something, that introduced a way of seeing that made the world larger, more interesting, more layered than it seemed before. We hope this journey has done something like that. The questions will remain. Where is everybody? What is the filter? Are we early or are we walking toward a wall? Is this cosmos fundamentally real, or is it something more like a dream dreamed by something we can't imagine? Are we alone, or simply the first, or simply the survivors of something that claimed everyone who came before? These questions don't demand resolution tonight. They ask only to be held, to be kept alive in the quiet background of a mind that is now beginning to let go of the day, to release the smaller urgencies and worries that filled the hours, and to drift toward that particular and valuable state of mind that sits between waking and sleeping, where thoughts are present but not gripping, where the self relaxes its insistence on solving things, where the large and the small can coexist without friction. In that state, the universe can feel different, less threatening and more strange in a good way, less like a problem to be solved and more like a landscape to be gradually, slowly, over a lifetime of looking, understood. The stars are out there right now. Wherever you are, the sky above you is full of them, even if you can't see them through walls and clouds. They've been burning since before your species existed. They'll burn long after. The Milky Way stretches above your planet in a sweep of 200 billion fires, each one ancient and each one temporary, the whole sweep of it belonging to a universe that contains hundreds of billions more such galaxies. You are a part of that. Not metaphorically, literally. Every atom in your body was forged in the heart of a star that exploded before the Earth existed. You are the cosmos, in a particular temporary arrangement, looking back at itself. The great filter, if it's real, is the test of whether that arrangement can last. Whether the universe's most interesting experiment can survive the dangerous phase of its own power. You are that experiment. Rest well tonight. Let the questions float. They will be here in the morning, patient and deep and still worth asking, and so will you on your pale blue moat in the great extraordinary silence of a universe that may be waiting for you to show it what comes next. The hour is late now, or the morning is very early depending on your perspective, which is perhaps an appropriate ambiguity for the end of a journey into the nature of reality and time. Let the last few thoughts arrive gently, like the last notes of something that was always meant to quiet the room. Life found its way on this world against extraordinary odds, through the Hadean heat of the earliest Earth, through the snowball Earth episodes when ice covered the equator, through mass extinction events that eliminated the majority of species alive at the time, through asteroid strikes and volcanic winters and the brutal competition of evolution. Through all of it, life persisted. It found its way into rock fissures and deep ocean vents, into polar ice and boiling springs, into the upper atmosphere and the deepest trenches. It absorbed every catastrophe and continued. That persistence is not a guarantee for us specifically. Species do go extinct. Civilizations have fallen. But the deep pattern of life on this world, its flexibility, its creativity in the evolutionary sense, its extraordinary willingness to occupy every possible niche, suggests something about the fundamental character of the process that produced us. It is not fragile in the ordinary sense. It is experimental, improvisational, relentlessly finding ways. We are not just the product of that process. We are also, in a novel way, its current agents. We can see the filters ahead. We can model the risks. We can coordinate around them in ways that no species before us could, because we have language and writing and mathematics and science and institutions that persist across generations. We have, for the first time in the 4 billion year history of life on this planet, the ability to look at the path ahead and make choices about which way to go. That is something genuinely new. Whether it is enough is the question, but it is something. The universe is old enough and large enough to produce nearly anything that its physics allows. What it hasn't produced, as far as we can tell, or hasn't produced yet, or hasn't produced visibly, is a civilization that cleared every filter, a species that made it through the dangerous adolescence of nuclear weapons and climate change and artificial intelligence and whatever other transitions await, and emerged on the other side. And you might be part of the one that does. That thought is worth carrying into sleep, not as a burden, as a quiet, orienting companion, a reminder, in the morning when the ordinary business of the day resumes, that the ordinary business of the day is part of something much larger than it appears. The silence of the cosmos may be an invitation, not to respond with noise, but to become, slowly and carefully and with open eyes, the kind of thing that deserves to be heard. The stars are listening.